Good afternoon, everyone. My name is Kai Zheng. I'm a postdoc from UC Berkeley Amp Lab, and this is my friend Samir, who is a software engineer from Databricks. So today we are very excited to share with you the latest project from Amp Lab and Databricks, which aims at delivering this online approximate OLAP in SparkSQL. So before I start off my talk, I would like to give you a brief intuition about the time scale when we are talking about doing OLAP queries on big data. Okay, so to be simple, let's assume a scenario that we have like a 100 terabyte data stored on 1,000 machines, and each machine just have a single disk, and we just want to do some kind of like simple aggregation on top of this data. So if the data, let's say, is fully stored on disk, and since the disk bandwidth is anywhere from 100 megabytes to 200 megabytes per second, so like doing the full processing would take you half an hour to 1 hour. And this latency is mainly incurred by the I/O time, and of course there are communication time and computation time. I mean, this latency is kind of okay for daily reports, but if if the user wants some like much more timely response, then it's better to use memory, right? Let's say now the data is fully cached in memory, and since the memory bandwidth is usually 100 times faster than the hard disk one, so doing the same thing will take you like 1 to 5 minutes. I mean, this latency is okay for hourly reports, but from these time scales, you can see that like OLAP, although has an online in its name, but actually nowadays it's far from being like fast enough to be online, right? So, and actually nowadays a large portion of these OLAP workloads are actually these kind of exploratory queries. So basically, I mean, for instance, like some data scientists wants to explore the data to get some to find out something like interesting unknown facts to support their decision making. And I mean, this kind of scenario usually involve many rounds of issuing query to the query engine and quickly check the result. So you can see that actually it really needs for quick and continuous feedbacks. But actually, I mean, nowadays the OLAP engine cannot meet with these requirements. And actually, one such solution called online aggregation has been long proposed in the database research area. Which can meet this kind of quick and continuous feedback requirement. And this online aggregation work was first proposed by Hurlstein, Haas, and Wang in their seminal paper published in Sigmod in the 1990s. So the basic idea of online aggregation is very simple. So let me explain it using a simple example. So now let's assume we have an example table. Let's say this is just a log of all the sessions across the whole country. And this table has 3 columns. Basically, we store the ID, the source city, and the latency of each session. Okay. Now we want to do some like simple analysis on this table. Let's say I just want to find out the average latency in a table. I mean, a traditional SQL engine would just process all the data, and after a long delay, it will give you a single exact answer. Let's say the answer is 34.667 here. But on the contrary, actually, online aggregation can give you fast answers as soon as it has processed part of the data. For instance, here, the engine just processed the first 5 tuples, and it can give you a quick response of some partial result, let's say 35 here. But at the same time, the query engine in the background will keep processing the data. Let's say the engine processed another tuple 6. So it can deliver you iteratively updated partial results. Let's say after I have processed the tuple 6, it will update the partial answer now it to be like 33.83. Okay, and if you let the engine keep processing the data until you finish all the data, then it will deliver you the same exact answer just as a normal SQL database will do. However, these partial answers are not very useful if it's not annotated with some kind of accuracy measure, because people want to know that how these partial answers, like how far these partial answers are from the exact true answer, right? So it's better to annotate some kind of error bars to these partial answers. And when you actually update the partial answers iteratively, you also iteratively refine the error bars, so you get more and more accurate estimate. So next, this talk will be about how we can deliver this kind of online aggregation interface integrated into the Spark stack, and and we provide support for general queries. So let me first go to the system design. So for those of you who are not very familiar with Spark, so basically Spark is a distributed computing platform which can utilize memory efficiently to do fast analysis. And SparkSQL is a SQL engine built on top of this distributed computing platform. So and in this talk we propose two new libraries on top of SparkSQL. So the first library is called GOLA, which stands for Generalized Online Aggregation, and another library called BlinkDB. So this GOLA library will give you this kind of continuous partial answers, and this BlinkDB library will give you continuous error bars. And in combination, they will provide like online aggregation kind of interface on top of SparkSQL. And next, I will show you how SparkSQL, how we expose this kind of online aggregation interface in SparkSQL. So here it's just some like snippet of codes showing you like how you do SQL now, like in SparkSQL. You do SQL queries now in SparkSQL. So basically, I mean, for those of you who are not very familiar with SparkSQL, there's this concept called SQL context in SparkSQL, which enables you to transform a SQL text into a concept called DataFrame. And you can think of this DataFrame as like RDD annotated with schema information. And if you call collect on this DataFrame, it will process through all the data and give you the exact query answer. So, but with this online interface, actually we can do this process iteratively, just like online aggregation. So the only thing you need to do is you call online on DataFrame, and this will return to you a new kind of DataFrame called online DataFrame. The power of this online DataFrame is that you can call collect next on this DataFrame iteratively, so it can give you iteratively refined partial answer along with their error estimations. And actually, you can fully automate this process by wrapping this collect next into a while loop. And you can see, I mean, it's very much like you are using an iterator. So basically, you iteratively call has next and collect next on this online data frame. So it will automatically go through the data set and delivering the iteratively updated results. And more interestingly, I mean, you can even have various stopping conditions in the while loop. So I mean, for those of you who have heard of BlinkDB, you know that BlinkDB provides the user with this kind of ability. So you can specify either a time limit on the query or an error limit on the query result. So we can easily support this kind of interface here by saying I want the response time to be smaller than 10 seconds, or I want the error bar to be smaller than 1%. Okay. But actually, the true power of this interface is that we can place the control into the hands of the user. So we can even say, we just run a query until the user actually cancels the query. So, and more interestingly, actually, we support more general queries than just the previous online aggregation work. So, I mean, besides this kind of simple aggregates, you can have aggregate for basic statistics, for example, like sum, count, standard deviation computed on data. You can even have user-defined aggregate functions, like whatever function written in some language like Java. And you can have arbitrary join group bys in the query. And you can even have nested queries. And this nested query could its own has a complex structures. Okay. So so the remainder of this talk will be divided into two parts. So the first part I'm going to talk about the Gola library. So like how we are able to deliver this kind of continuous answers. And the second part, which will be given by my friend Samir, who will talk about how we can deliver this kind of continuous error estimation by using the BlinkDB library. Okay, so so now let's get into the details of the Gola library. So actually, the key idea of Gola, which enables it to deliver this continuous partial answers, is that we introduce delta maintenance as a first-class citizen in query execution. So now let's look into query execution and see like what is really happening under the hood. Okay, so if you are familiar with SQL, then you know that nowadays the SQL engines will take a SQL query, let's say the simple aggregate query on the left, and it will first transform it into a query plan, and then run this query plan on the data, right? So for instance, this simple aggregate query will be transformed into a query plan, something like this, consisting of like 2 operators. So basically, you first take in the log table and run a scan operator on top of it, scan through all the tuples, and then all these tuples will be fed into the aggregate operator, which will compute the average latency. And of course, I mean, if you have a much more complex query, then the query plan will be more complex. For instance, here we have a nested aggregate query. Basically means that like I have an inner query which computes, we have an inner query which computes the average latency, and we use this average latency as a threshold to filter out the tuples in the log table, and then we only compute the average latency on these selected tuples, right? And on the left is the corresponding query plan. And you can see here we still have the corresponding part for this inner subquery, which computes the average latency, and then this average latency is joined with the log table, filtered, and fed into another aggregate operator. So, and as far as the data is concerned, so you can think of like the log table is actually, so in the system is actually divided into many partitions, and these partitions are distributed in a very balanced way across the cluster. For instance, here, let's say I have a 3-node cluster, just for example, and I mean these partitions are evenly stored on all of these nodes, either in disk or cached in memory. So and so when it comes to query execution, so the traditional SQL database will do something like this. So it will take all the partitions, all advanced at the beginning, and then process through it, and only after all the processing has done, it will return you a single answer. But on the contrary, so our SparkSQL with online aggregation kind of interface will do something different. So we will actually chop up the input partitions into multiple chunks, and each chunk could consist of 1 or more partitions. And then we just run the same query on all of these chunks one by one. Okay. For instance, we will take the first chunk, run the query, and it will give you some partial answer as soon as I finish processing these, the first chunk. And besides the partial answer, we will also deliver some kind of intermediate state. And this intermediate state will be combined with the next partition and fed into the next query. Okay. So the input to the next to this iterative queries, we call it delta input. And we can see that the delta input here has 2 parts. So one part is the new data. The other part is the intermediate states from the previous query, right? And you can iteratively, repeatedly do this. And actually, so how to do this kind of delta computation has been intensively studied in database research. For example, in the context of delta view maintenance, right? So, and actually, people already find out that actually the key point to make this thing really efficient is to actually minimize the size of the intermediate state. So I will give you like a brief intuition about what an intermediate state could look like. So for example, let's pick this simple aggregate query. So here the intermediate state is actually very straightforward. So you only need to keep the running sum and the running count of the latency column, and then like you can always compute the running average from this internal like intermediate state. However, if you have a more involved query, for instance, this is our previous nested aggregate query. Actually, it's very hard to find out what the intermediate states could look like. So actually, the true problems lies in here. If you look at this inner subquery, I mean, since this query is computed on partial data, so across different iterations, the partial result given by this inner query could change, right? And whenever the partial answer is changed, then you have to join it with all the tuples you have seen previously, redo the join, redo the filter, and redo the outer aggregate again. So basically, you will find out actually the intermediate state is all the data you have been processed in all the previous iterations, which, I mean, it's obvious that this solution is far from optimal because the size of the intermediate state grows linearly with the number of iterations, and therefore, like, you get longer and longer latency for each updated iteration. So, however, like our Gola library will use a completely different update algorithm. So we proposed this algorithm in Sigma 2015. So for people who are interested in our algorithm, you can check out our paper. So basically, the idea is that for each result tuple produced by any intermediate operator in the query plan, we simply analyze like whether this tuple will change across different iterations, and whether this change will affect the partial answer like you will deliver. And we only track those tuples that can change, and the change can actually impact the output result. So, so for instance here, so all the blue parts either won't change, or like their change won't impact the output, the outcome of the query. So we only need actually to track the data marked in yellow here. So next, I will use the example, to give a more intuitive explanation. So again, let's look at this nested query we used before. So we know that after the first iteration, the inner query is evaluated to 35, and if we process more data, let's say tuple 6, then the inner query is updated to 33.83. And if you look at this tuple, like tuple 3 here, we will find out actually it will be filtered out in the first iteration because its latency is smaller than 35, but it will be selected in the next iteration because its latency is larger than 33.83. So basically, we are not sure about whether this tuple will in or not. And you can see that this change will actually impact tuple 3 because it actually determines whether tuple 3 will contribute to the outer average query here. So, however, let's say if you can get some analysis about the inner query. Let's say from the partial result I have processed, I find out like this inner average will fall within this range. Let's say 35 plus minus 1.5. Then we can do more clever things. Actually, so how to get this analysis will be talked about by my friend Samir. So now let's see how we can utilize this estimation we get. So if you look at the tuple 1, since its latency is outside of this variation range, so basically means that we have high confidence about like this tuple 1 will be always filtered out even in the future iterations. So it will never contribute to the outer query. And also similarly, if you look at the tuple 2 and tuple 5, their latency are also like outside the variation range, and actually it's even larger than the upper bound of the variation range. So basically means that we have a high confidence that this tuple will always be selected, and they will always contribute to the outer query. So, and the only thing we are not sure is actually only tuple 3 and tuple 4 here, because their latency value actually fall into the variation range. And therefore, we call them uncertain tuples. And this is exactly the intermediate state we want to keep track of. So, and in terms of the update plan, it looks something like this. So you don't need to look into the details, but basically means that for this filter, we will keep track of those uncertain tuples, And we also need to keep track of the running sum and running count for both the inner aggregate and the outer aggregate. And these three things together in combination will make intermediate state, which will be fed into the next query. Okay, so in summary, we can see that actually our Gola library, I mean, the key difference here is, besides optimizing the query latency here, our Gola library will also minimize the intermediate state to speed up the delta maintenance. And however, if you look at each delta update query, they are just normal SQL queries, which means that they can be optimized using the Catalyst compiler in SparkSQL, and therefore is able to use all existing optimizations, all existing SQL optimizations. And each of these delta update query will be compiled into a distributed Spark job, which means that it can fully utilize the parallelism in a cluster, and you get fault tolerance and load balancing for free from the Spark platform. So next, my friend Samir will talk about how to do continuous error estimation in BlinkDB. Okay.
So hi, everyone. Next, I'll be basically focusing on getting incremental error bars on these continuous answers. And then essentially towards the end, we think that you would really realize the powerful nature of this framework when we actually show you a live demo. So essentially, in the demo, we'll show you how these so-called, fairly complicated sounding techniques can actually be applied to a very, very wide range of queries to get these continuous answers augmented with error bars. So okay, so just to basically put things in context, this is the example that Kai showed you before, which is, it's a table, it's a session table, which has 3 columns. It has a session ID, it has a city where the session originated, and it has some latency metric. And you would basically want to ask a query of what is the average latency in this table, which might return an exact answer in a long, long time that might look something like this. Now, if you operate on a partial data, you get a partial answer, an approximate answer. Now, this answer in itself might not be entirely useful because you do not actually know how far is this answer from the true answer. So in order to essentially add value to the corresponding result, we also augment these answers with numerical error bars. Now, what these error bars look like is something like this. So essentially, after the first 4 rows, you actually see an answer which looks like this, which is 34.5 plus minus 2.0. Now, depending on what your use case is or what you're trying to do, maybe this answer is good enough for the analysis that you're trying to make or the kind of things that you want to process. If not, you can always go on and process more and more data. The answer will get more and more accurate, and the error bars would go smaller and smaller. So how do we calculate this error bar? Now, there has been a lot of work done in both the statistics and the database community in actually calculating these error bars on samples of data. Now, I don't want you to actually go into all the details, but just from a very, very high level, right? So there is something called as the central limit theorem for basic samples. And what the central limit theorem says is that there are these set of aggregates. There are these sets of standard aggregates, count, sum, mean, variance, standard deviation. If your query contains any of these aggregates, you can simply calculate the error that's associated with a query execution on partial data by just putting these values. And these are just values about the sample size, maybe in some cases the variance of the sample, the mean of the sample, and so on. You can just plug and play these formulas and calculate the approximate error that you basically incur on the sample. On the right-hand side, we have a relatively newer method, and by relatively, I mean it's still 30 years old, of error estimation using a method called Bootstrap. Now, statistical Bootstrap is a method that basically can give you the error estimate for a wide range of queries. So unlike central limit theorem, your error estimation methods or your error estimation aggregates need not be just limited to the 5 things that I have mentioned here. They could actually have UDAFs, like user-defined functions or aggregate functions. They could even have where clauses, joins, filters, anything that your query has, nested subquery structure. You can actually use these Bootstrap techniques to calculate the error that's associated with a particular sample of data. Right? So for generality of these techniques, we actually chose to implement this in SparkSQL and BlinkDB instead of the closed forms. So let me give a brief intuition of how Bootstrap works, just with an example. So see the original table, right? And in this table, I basically want to calculate the error that's associated if I basically process the first 4 rows of this table or this sample. Now what Bootstrap says is that we create a resample with replacement of exactly the same size as my original sample. So what this means is I'm actually creating my first resample. It has size of 4. It's created with replacement. So if I basically pick a row and put it in the resample, I actually have to place it back. So it's always possible to pick a row twice or more than once. Now when I get this resample, I execute my original query, which was the average latency query, on this resample of data. And I get my first so-called point estimate, in which case this is the average of 34. I similarly repeat this process. I create another resample. I execute my query on this another resample. I get another point estimate. And Bootstrap basically says that if you do it a lot of times, in this case, let's say I do it 100 times, I can actually get a range of point estimates, or these so-called aggregates or averages. Now, as far as the method is concerned, it says that the range of these aggregates, so the range of these aggregates in this just toy example is 32.5 to 35. This variation range can actually give you an estimation of the error that's associated with the query if it operates on the original sample of data. So if I have a query that operates on the original sample of data, I can figure out this error bar of ±2 by looking at the range of these variation ranges that each of these point estimate returned. So this is, in a nutshell, is like how Bootstrap works. However, there was a problem here, right? Essentially, if I were to do incremental maintenance or incremental delta maintenance, if I get another tuple, these tuples in each of these resamples are highly correlated. So I cannot actually keep any of these resamples that I created for the first 4 rows. I have to completely discard them, create another set of like resamples for this like new 5 set of rows, run my query like 100 times or like more on each of these resamples once again, and create an updated error bar. Now, once again, if we actually do this, this would basically say that every time I'm actually computing a delta update, I have to recompute my error bar like on everything once again, incurring like quadratic overhead, which is not like feasible. So what we did, we basically proposed this technique called Poissonized resampling to essentially generate samples with replacement. And again, I mean, if you want to actually go into a little bit more statistical details, you're most welcome to read our Sigma paper last year. But I'll just give a brief intuition of how this technique works. So as far as this technique is concerned, this says that while I am actually executing the query, I can sample from a given Poisson distribution and then figure out an approximation of the multiplicities that would be associated with each row when I am actually computing the resample. So essentially, these multiplicities of 2, 1, 0, 1, 1 could be a good approximation of the multiplicities that I would have gotten in the first resample of my data. Now, why this technique is actually extremely useful is because it works iteratively. So essentially, if I'm processing on more and more data, so if I process on the 6th row, I pick the 6th row, I sample from a Poisson distribution, and add the multiplicity for that resample of data. So I can actually construct all these resamples iteratively in my queries. Similarly, I can also construct all these resamples in a single pass. So essentially, if I were to construct all these 100 resamples in a single pass, I look at row 1, I sample 100 times from a Poisson distribution, construct these samples, move on to the 2nd row, and kind of like, I mean, as like Gola, or Generalized Online Aggregation Library, is giving us continuous answers, we can give these continuous incremental error bars in each of these resamples of data. Now, while this is able to construct all these resamples in a single pass, for those of you who are actually familiar with the JVM performance, one of the disadvantages of evaluating such an expression is that it's extremely expensive, right? In other words, if you look at this expression, rsum, which basically maintains a running sum for calculating a running average, and it basically computes the latency, which was the 3rd column in my table, with the corresponding multiplicities of each of my resamples. This expression, which actually gives me the first point estimate, and then I have to do it like 100 times, actually incurs a lot of overhead into the JVM. This overhead normally comes because of a large number of like virtual function calls. Then there is this like boxing overheads, memory overheads due to boxing, and so on and so forth. So for example, if I look at this simple Bootstrap query I have, like this essentially calls or sends a virtual call to add.eval, which in turn kind of like sends a call to our sum.eval, and then multiply.eval, our sum returns a box double, multiply in turn goes recursively down the tree. So essentially, all in all, this is extremely expensive as far as evaluation is concerned. So one of the first things that we did, essentially similar to SparkSQL, we heavily make use of Scala quasi-codes and runtime reflection to essentially generate the bytecode at runtime. And this actually helps us, Scala quasi-codes, helps us easily manipulate the Scala AST and match on any of these attributes in order to generate these highly, highly optimal codes that we basically use to optimize our Bootstrap. In all, what we actually get is that if we have a simple statement that actually executes Bootstrap, we can actually consolidate all the Bootstrap in a tight for loop. We can completely do away with any of the boxing costs. And we also kind of minimize a large number of virtual function calls. So all in all, this is what we did to make Bootstrap as a procedure and really, really fast. In terms of each iteration, we actually use this to bring down the time of each iteration down from probably tens of seconds to just a few seconds. And we will show you later in this talk. So just to summarize, there is one takeaway. If there is just one takeaway that we would want to give as part of this talk, is that online approximation, giving these answers continuously with error bars is becoming a more and more important means to achieve interactivity in processing large data sets. It does not actually modify your internal SQL query engine at all, right? Essentially, while you're waiting for answers, you just get something extra out of it, right? It's up to you to cancel the execution or still just basically go ahead and execute the whole query. And towards this end, we actually are working on these two libraries. First of all, we basically presented generalized online aggregation, which actually returns these continuous answers as you operate on more and more data. And then we propose this BlinkDB library, which basically returns and augments these continuous answers with continuous error bars. So next, I think let's show a demo, and then we kind of just conclude. Hopefully the Wi-Fi works. Okay, so I'll just give a brief introduction of what this is. This is just the database cloud, but essentially the high-level thing is it's just a Spark shell that we have, and it just makes it easy to load the data. But underlying, it's actually running the Spark open source version that we have, right? So what I have here is just a SQL shell, and I have a table with me, which essentially is called anon SDM SS 5%, right? And this table has around 100 columns. This is very similar to a real-world session log table, which we showed in the toy example. This basically records the session information for each of the users that we have in our database. So essentially, this information might be when the user joined, or what is the buffering ratio, what is the latitude, longitude of that user from which the session originated, and so on and so forth. So we have all this information there, right? And now what we would like to show you is some simple queries that can actually show you these systems operating live. So first of all, let's say that we want to basically calculate or execute a query for figuring out what is the average join time. Join time is just a field or a column in this table for all these queries in the session. So if we run this query, that basically, first of all, it just compiles the query, and then it will just execute the query in an online fashion. So if you see this, essentially this is just underlying executing a query. And what you see here is that you're seeing three things. And again, this is just basically the corresponding results that are running. And these three things, if I would expand it, is essentially point estimate. So point estimate is basically, you can think of it as an approximate answer. So when we ran this query for, let's say, just maybe 5 seconds, we got this as an approximate answer. So this is the average approximate join, 10.15. The confidence interval lower just means the lowest value. We have basically bounded the error that is around this answer that we returned. So all in all, this first query basically means that your answer is between 9 to 11, I think. Yeah. So it's 9.6 to 10.98 seconds, right? So similarly, we have like different queries that we can show. Like if you see, if like essentially while you are running these queries, these point estimates or these answers, these approximate answers are actually like updating on the fly, right? And again, like I mean, if you keep the query running, you actually get like what you get from like any database right now. Like I mean, essentially you are getting like the exact answer with like so-called 0 error. But it's all about like getting feedback while your query is running. And this is what like this system enables. So again, like I mean, I don't know, like I mean, if like this would actually work, because this is actually doing a lot things. So this is actually one of the really complex queries that we want to demonstrate, and we are kind of like really keeping our fingers crossed. So let's actually spend time on what this is doing first of all. This is like a UDAF, like a user-defined function that we have in our that we have registered. And I mean, this is just like simply an approximate median function. It kind of like bins your data into bins, and then essentially tries to compute what is the approximate median, right? For all practical purposes, it's a UDAF. Now, what I have here is essentially a really complex query. And if you actually see this query, it has two levels of like nesting. So essentially, there is a nested query inside this query. So I mean, you can see a select on that inside query. That in turn is calling like this UDF, right? So essentially, there is a query that internal, and it's trying to call this UDF. And then there is another query, which is like below this, that's like essentially calling some aggregate internally. So I mean, kind of like, I mean, the kind of query that we had in our talk, which actually talks about a lot of these kind of things, which is that, I mean, queries with like really deep nested structure, computing like user-defined aggregates on these kind of things, along with like simple aggregates and like all these kind of things, right? So essentially this query, if you go down, like, I mean, can you kick this query? It might take some. So this query essentially is so complex that SparkSQL essentially takes some time to compile this in a query plan. So we'll see like when this query actually begins execution, when these like kind of like rolling error. Okay, so now it begins, right? So essentially, now you see, like, I mean, essentially it's a group by query, so it's actually like returning a lot of things. And as this query is running, it's actually returning these point estimates which are updated. So essentially, I mean, this is a group by query, so not everything is updated like right away. But I mean, as this query runs more and more, you can actually see these point estimates. So now it has refreshed. And it will again refresh, like if you basically, yeah, so again refreshed. Yeah. Okay, thankfully it worked. So now, I mean, as you can see, like, I mean, essentially this technique of online aggregation is actually fairly generally applicable to a wide range of queries. And this is pretty much what we wanted to convey in this talk. So just to conclude, if I can have the slides back. Okay, I just have like one last slide, which is that we already have like open source of code, like in a limited preview mode, to a lot of like early adopters. Please, if you want to check it out, or like, I mean, actually like submit pull requests, please send us a mail to either like Kai or me or both of us to actually like get access to our repository. It has like all the code that we actually demoed today, and kind of like, I mean, builds on both Spark 1.4 and 1.3. So whichever package whichever Spark version you're using, you can actually like look at the code. We are also very soon releasing a Spark version, a Spark package. So Spark package would just allow you to actually like import all of this code as a library and just use with the Spark versions that you're using. And then finally, a lot of this thing would make it to native SparkSQL integration in 1.5, which is due to release in September, 1.6, and like beyond that. With that, we conclude our talk, and thank you. Okay. Yeah, that's right. Yeah.
Hello. Yeah, it's almost on. Hello. Doesn't work? Oh.
Maybe I can take it offline.
Yeah, we can take questions off.
Can I ask?